Hello everyone. Today we'll study continuous random variable. Before I introduce what it is, let's look at an example first. Consider an experiment of randomly choosing a real number between 0 and 100. Let the random variable x represent the value of the chosen number. Find each of the following probabilities. Part A, probability that s equal to 1. Part B, probability that s equal to 10. Part C, probability that s is between 0 and 50. Part D, probability that s is between 20 and 40. How do I find the probability here? We randomly choose a number from 0 to 100. From 0 to 100. Randomly choose a number from 0 to 100. What's the probability of getting 1? What's the probability of getting 1? We can think of an old technique. Probability is number of favorable outcome divided by number of all possible outcome. Number of favorable outcome, s equal to 1. There's only one number. 1 is here. There's only one such number. So number of favorable outcome is 1. What's the number of all possible outcome? Between 0 and 100, how many numbers do we have? 0, 1, 2, 3, 4, 5, about 100, but there are more than 100 numbers. Think of 0.1, 0.2, 0.3, 0.001, 0.01, 0.001, 0.001. Between 0 and 100, there are infinitely many real numbers. Between 0 and 100, there are infinitely many real numbers. So we can think of 1 over infinity, that's 0. So probability of choosing number 1 is 0. That's impossible. If we choose a number randomly, probability of getting 1 is 0. Part B. What's the probability of getting 10? What's the probability that s equal to 10? When we choose a number randomly from 0 to 100, what's the probability of choosing 10? If we use an old technique, we can think of that number of favorable outcome divided by number of all possible outcome. Number 10 is one of the real number between 0 and 100. So there's only one favorable outcome. There's only one favorable outcome. How many possible outcomes are there? Between 0 and 100, there are infinitely many real numbers. Between 0 and 100, there are infinitely many real numbers. So 1 over infinity is 0. The chance of getting 10 is almost impossible. Between 0 and 100, if we choose a number randomly, the chance of getting number 10 is almost impossible. So the probability is 0. Part C. What's the probability that s is between 0 and 50? What's the probability that s is between 0 and 50? If we use an old technique, think of number of favorable outcome divided by number of all possible outcome. Between 0 and 50, there are infinitely many real numbers. Between 0 and 50, there are infinitely many real numbers. And also, between 0 and 100, for the denominator, number of all possible outcome. Between 0 and 100, below 0 and 100, there are also infinitely many real numbers. We get infinity over infinity. It makes nonsense. We get infinity over infinity. It makes nonsense. Now what should we do? Now, we know that if we choose a number randomly between 0 and 50, if we choose a number randomly between 0 and 100, the chance that the number is between 0 and 50 is half, right? Half. We know the answer is half, but how do we get half? We know that if we choose a number randomly, the chance that it's between, if we choose a number randomly from 0 to 100, the chance that it's between 0 and 50 is half. Half. It's 50-50, half. But we know the answer is half. But how do we get half here? How do we get half here? So, in this situation, we think of probability in a different way. Let's try to use area represent probabilities. When we choose a number between 0 and 100, every number has the same chance to be chosen. So every number have the same chance to be chosen. Probability is the same everywhere. Probability at 0, 1, 2, 3, 4, 5. Probability is the same everywhere. Think of area. Assume we know that the total probability is 1. Assume the total area here is 1. Assume the total area under this curve is 1. We try to use area to represent probabilities. Assume the total area under the curve is 1. This is a rectangular region. The length from 0 to 100 is 100. The length is 100. And what's the width? What's the width here? The area is length times width. If we know the area, the total area must be 1. The length is 100. What's the width should be? What the width here should be? Solve the equation for width. Width must be 1 over 100. So this width here must be 1 over 100. That's the width. Length is 100. Width is 1 over 100. Then length times width is 1. That's the total area. Now let's use area to represent probability. If S is between 0 and 50, think of an area under the curve from 0 to 50. What's the area here? Area under the curve from 0 to 50. What's the area here? Area is, for this area here, how do we find this area? For x between 0 and 50, let's think of area under the curve. Length is 50. Width is 1 over 100. Area is length times width. 50 times 1 over 100 is 50 over 100, which is half. So if we choose a number randomly, the chance that the number is between 0 and 50 is half. If we choose a number randomly, the chance that the number is between 0 and 50 is half. If we choose a number randomly from 0 and 100, the chance that the number is between 0 and 50 is half. Part D. What's the probability that S is between 20 and 40? What's the probability that S is between 20 and 40? 20 is somewhere here. 40 is here. Think of area between 20 and 40. Think of area under the curve between 20 and 40. Think of area under the curve between 20 and 40. This is a rectangular region. Area for rectangle is length times width. From 20 to 40, length is 20. Width is 1 over 100. Length times width. 20 times 1 over 100 is 20 over 100, which is 1 over 5. So we can use area to represent probabilities. That's the idea of continuous random variable. Using area to represent probabilities. That's the idea of continuous random variable. Next, let me give you the formal definition. Continuous random variables. Let x be a random variable. If there exists an integrable non-negative function non-negative function f of x such that for all closed interval AB, probability that S is between A and B, this is capital X, probability that S is between A and B equal to the integral from A to B f of x dx. Then x is called a continuous random variable. And the function f is called the probability density function. Probability density function. PDF. We use PDF to represent probability density function. Then function f is called the probability density function of x. We use PDF to represent probability density function. Next, let me show you some properties about continuous random variable and the probability density function. Let x be a continuous random variable. Let x be a continuous random variable with probability density function f of x. Then we have the following properties. First property, probability that s equal to a is always 0. Probability that s equal to a is always 0 for all real number a. Probability that s equal to a is always 0 for all real number a. Probability s equal to a is the integral from a to a f of x dx. Probability s equal to a is the integral from a to a f of x dx. This integral is always 0. Next, probability that x between a and b, that's the same as probability that x between a and b including a, not b. The same as probability that x between a and b including b but not a. The same as probability that x between a and b not including a and b. They are all the same. They all represent the integral from a to b f of x dx. They all represent the integral from a to b f of x dx because they all represent area under the curve from a to b. they all represent this area here. For the first probability here, x between a and b, including a and b, we include these two lines. But if we include the boundary, area stays the same. It doesn't matter if we include the boundary or not. Area under the curve stays the same. So if I don't include b, if I don't include this boundary, the area under the curve must be the same. So this integral is the same as this integral. But if I include same thing if I include b, not including a, area is the same. If I don't include both a and b, the area under the curve still the same. It doesn't matter if we include the boundary or not. Area under the curve stays the same. So they are all the same. They all equal to integral from a to b f of x dx. They are all the same. These four probabilities, they are all the same. They all equal to the integral from a to b f of x dx. Next, probability that x less or equal to a. Probability that x less or equal to a. That's the integral from net infinity to a f of x dx. Probability that x less or equal to a is the integral from net infinity to a f of x dx. And similarly, probability that x is greater or equal to a is the integral from a to infinity. Probability that x is greater or equal to a is the integral from a to infinity f of x dx. Next, the integral from net infinity to infinity f of x dx. Since f of x is a probability density function, the area under the curve represents probabilities. The total probability must be 1. That means the total area under the curve must be 1. Since area under the curve f of x represents probabilities, the total probability together must be 1. So the total area under the curve, from net infinity to infinity must be 1. And probability density function must always be greater than or equal to 0. Probability density function must always be greater than or equal to 0. Those are the properties about continuous random variable and probability density function. Note: don't be confused. Probability function, probability density function, and probability function, they are not the same. A probability density function is not a probability function. A probability density function is not a probability function. Be very, very careful. A probability density function is not a probability function. Because for probability function, f of x, for a probability function f of x, it must be between 0 and 1. And the sum of f of x for all x in the support must be 1. For probability function, there are two properties. F of x must be between 0 and 1. And the sum of f of x for all x in the support must be 1. Probability density function, f of x must be greater than 0. It may be more than 1. And the total probability integral from net infinity to infinity must be 1. They are not the same. A probability function is not a probability density function. They are not the same thing. A probability function may be more than 1, but probability function probability density function f of x, it may be more than 1. It may be more than 1. But a probability function f of x, it must be between 0 and 1. They are not the same. And also, for probability function, the sum of f of x for all x in the support must be 1. And for probability density function, the integral from negative infinity to infinity f of x dx must be 1. So they are not the same thing. Don't be confused. A probability density function is not a probability function. Next, let's look at an example here. Let x be a continuous random variable with probability density function f of x equal to cs squared if x is between 0 and 6 and 0 otherwise. Part A, find the value of c. Part B, find each of the following probabilities. Probability that s is less or equal to 1. Probability that s is greater than or equal to 3. Probability that s is between 2 and 4, including 4. Probability that s is equal to 4. Find each of the following probabilities. So let's find C first. We know that the total probability must be 1. So the integral from negative infinity to infinity, f of x dx, it must be 1. This integral must be 1. If we take this integral, we know that f of x is between 0 and 6 is cs squared and 0 otherwise. That means we only take integral from 0 to 6. The rest is 0. We only take integral from 0 to 6, cx squared dx. The rest is 0. Then solve this integral. We have cs cubed over 3. Take antiderivative with respect to x. cs cubed over 3 from 0 to 6. If I plug in 6 cubed is 216. 216 divided by 3 is 72. I get 72c. If I plug in 0, I get 0. So this integral equal to 72c. And we know that the total probability must be 1. If I set 72c equal to 1, then solve the equation for c. If I set 72c equal to 1, solve the equation for c. C is 1 over 72. That's part A. Find the value of c. Part B. Find each of the following probabilities. Probability that x is less or equal to 1. Probability that s is less or equal to 1. Between 0 and 6, if s is less or equal to 1, we take integral from 0 to 1. It's 0 otherwise, so take integral from 0 to 1. In this interval, if s is less or equal to 1, take integral from 0 to 1. Take integral from 0 to 1, f of x dx. Take integral from 0 to 1, f of x dx. If I take antiderivative, that's cs cubed over 3. Evaluate from 0 to 1. If I plug in 1, I get 1/3 of c. If I plug in 0, I get 0, which is 1/3 of c. And we know that c is 1 over 72. So that's 1 over 216. Next, probability that s is greater than or equal to 3. In this interval, from 0 to 6, if s is greater or equal to 3, we take integral from 3 to 6. If x is greater or equal to 3, we take integral from 3 to 6. Cx squared dx. Take antiderivative. We have cs cubed over 3. Evaluate from 3 to 6. If I plug in 6 cubed is 216. 216 over 3 is 72. I get 72c. If I plug in 3 cubed is 27. 27 take away 3. Sorry, 27 divided by 3 is 9. So I get 9c. 72c minus 9c is 63c. And we know that c is 1 over 72. Plugging, we have 63 over 72. Divide top and bottom by 9. That's 7 over a. So the probability that s is greater or equal to 3 is 7 over a. Next, what's the probability that x is between 2 and 4, including 4, but not 2? So when s is between 2 and 4, it doesn't matter the endpoint is included or not. Take integral from 2 to 4. F of x dx. Between 2 to 4, f of x is cx squared. Between 2 to 4, f of x is cx squared. Between 2 to 4, f of x is cx squared. So plug in cx squared for f of x. Take antiderivative. We have cs cubed over 3. Evaluate from 2 to 4. If I plug in 4 cubed is 64. I get 64c over 3. If I plug in 2 cubed is a. I get ac over 3. 64 take away a. 64 take away a is 56. So the answer is 56 over 3 times c. And we know that c is 1 over 72. c is 1 over 72, so I can plug in 52 over 3. 56 over 3 times 1 over 72. For 56 and 72, I can divide both numbers by a. I get 7 here. 9 times 3 is 27. So probability is 7 over 27. Next, what's the probability that s equal to 4? Probability that s equal to 4. That's the integral from 4 to 4. cs squared dx. This integral is always 1. Integral from 4 to 4 is 1. So it's always 0. Integral from 4 to 4 is always 0. There's no area under the curve from 4 to 4. There's no area under the curve from 4 to 4. So the probability is 0. Probability that s equal to 4 is 0. For any probability density function, the probability that s equal to a constant is always 0. For any probability density function, the probability that s equal to a constant is always 0. Next example, let the continuous random variable x represent the lifetime of a battery measured in hours. With probability density function f of x equal to c times e to the power of negative x if s is greater or equal to 0. 0 otherwise. Part A, find the value of c. Part B, what's the probability that a battery has a lifetime of 3 hours or more? Part C, what's the probability that a battery has a lifetime of 1 hour or less? Part D, what's the probability that a battery has a lifetime between 2 and 5 hours? So let's do part A first. Find the value of c. We know that the total probability must be 1. So the integral from negative infinity to infinity, f of x dx, it must be 1. And the function f of x is c times e to the power of negative x if s is greater than or equal to 0, and 0 otherwise. So we take integral from 0 to infinity. When s is greater than 0, take integral from 0 to infinity. When s is greater than 0, we have c times e to the power of negative x dx, and it's 0 otherwise. The rest is 0. Take integral from 0 to infinity, c times e to the power of negative x dx. Then take antiderivative. Take antiderivative for c times e to the power of negative x. I have negative c times e to the negative x from 0 to infinity. If I plug in infinity, e raised to negative infinity is 0. E raised to negative infinity is 0. Exponential function looks like this. When s goes to 0, when s goes to 0, when s goes to negative infinity, when s goes to negative infinity, the function goes to 0. So e raised to negative infinity is 0. If I plug in 0, here, e to the power of 0 is 1. If I plug in 0, e raised to the power of 0 is 1. So we get 0 minus negative c times 1, which is c. And since the total probability is 1, c must be 1. Since the total probability is 1, c must be 1. Since the total probability is 1, c must be 1. That's part A. Now part B. What's the probability that a battery has a lifetime of 3 hours or more? What's the probability that a battery has a lifetime of 3 hours or more? So for part B, we are looking for probability that s is greater than or equal to 3. For part B, we are looking for probability that s is greater than or equal to 3. When s is greater or equal to 3, it's obviously greater than 0. So we use the function c of c times e to the power of negative x. So take integral from 3 to infinity. When s is greater or equal to 3, take integral from 3 to infinity. C times e to the negative x dx. Here we know c is 1. Since c is 1, 1 times e to the power of negative x is e to the power of negative x. Since c is 1, I can write 1 here. 1 times e to the power of negative x is e to the power of negative x dx. Then take antiderivative. Take antiderivative, I get negative e raised to negative x from 3 to infinity. If I plug in infinity, e raised to negative infinity is 0. If I plug in 3, I get negative e raised to negative 3. Double negative is positive, so the answer is 1 over e to the power of 3. The answer is 1 over e to the power of 3. Part C. Part C. What's the probability that a battery has a lifetime of 1 hour or less? What's the probability that a battery has a lifetime of 1 hour or less? In this interval, s is from 0 to infinity. If s is less than 1, we take integral from 0 to 1. In this interval, s is from 0 to infinity. If we are looking for probability that x is less than or equal to 1, take integral from 0 to 1, because this part, its probability is 0. In this part, probability is 0. So only take integral from 0 to 1. Part C, we're looking for probability that x is less or equal to 1. A battery has a lifetime 1 hour or less. For probability s less or equal to 1, in this interval from 0 to infinity, this part is less or equal to 1. So take integral from 0 to 1. And the function here is c times e raised to negative x dx. Since c is 1, I can drop c. I get e raised to negative x dx. Then take antiderivative. If I take antiderivative, I get negative e raised to negative x. Evaluate from 0 to 1. If I plug in 1, I get e raised to negative 1. If I plug in 0, I get negative e to the power of 0. e to the power of 0 is 1. The first part is negative 1 over e. Second part is plus 1. So the answer is 1 minus 1 over e. Probability that s less than 1, less or equal to 1 is 1 minus 1 over e. Part D. What's the probability that a battery has a lifetime between 2 and 5 hours? What's the probability that a battery has a lifetime between 2 and 5 hours? We're looking for probability that s is between 2 and 5. S is between 2 and 5. Here, take integral from 2 to 5. Well, s is between 2 to 5. Well, s is between 2 to 5. S is greater than 0. So we use the first function. C times e to the power of negative x. And we know c is 1, so we can drop c. Let's integral from 2 to 5. E to the power of negative x dx. Take antiderivative. We get negative e raised to negative x. Evaluate from 2 to 5. If we plug in 5, negative e raised to negative 5. If we plug in 2, negative e raised to negative 2. Then simplify. That's negative 1 over e to the power of 5. Double negative is positive. 1 over e to the power of 2. That's 1 over e squared minus 1 over e to the power of 5. That's the probability that the lifetime of the battery is between 2 and 5 hours. Next, let me introduce a probability distribution called continuous uniform distribution. Continuous uniform distribution. In an interval, a closed interval from alpha to beta. In a closed interval from alpha to beta, a number is randomly chosen from the interval. A number is randomly chosen. Assume the chance of choosing every number is the same. Assume the chance of choosing every number in the interval is the same. Assume the chance of choosing every number in the interval is the same. Let the continuous random variable then the continuous random variable x represent the value of the chosen number. Then the continuous random variable x represent the value of the chosen number. Then we say x has a continuous uniform distribution. Then we say x has a continuous uniform distribution. the probability density function of x. What's the probability density function of x? What's the PDF of x? What's the probability density function of x? We know that we randomly choose a number from the interval alpha to beta. Every number have the same chance to be chosen. Every number have the same chance to be chosen. In the interval, every number have the same chance to be chosen. So probability must be the same for every number. Since every number have the same chance to be chosen, probability for every number must be the same. The probability of choosing every number is the same. And the chance of choosing the number outside the interval is 0, because we only choose number in the interval from alpha to beta. The probability of choosing a number outside the interval is 0. And the probability of choosing a number in the interval is the same everywhere. We know that the total probability must be 1. The total probability must be 1. And this is a rectangular region. This is a rectangular region. For area of a rectangle, we can use length times width. Length times width. What's the length here? What's the length from alpha to beta? The length from alpha to beta is beta minus alpha. The length from alpha to beta is beta minus alpha. What's the width here? What's the width here? We know that total area is length times width. We know the total area must be 1. The total probability must be 1, because there's no probability outside the interval. All probability is here. The total probability must be 1. Length is beta minus alpha. What's the width? For the width, we can use 1 over beta minus alpha. For the width, we can use 1 divided by beta minus alpha. So the width here is 1 over beta minus alpha. This is a horizontal line. This is a horizontal line. The function for a horizontal line must be a constant function. The function of a horizontal line must be a constant function, and the constant is the height of this rectangle. So f of x is 1 over beta minus alpha. This is a constant function. For any horizontal line, the function is a constant function. And this constant here is the height of the rectangle, which is 1 over beta minus alpha. So f of x is 1 over beta minus alpha. So f of x is 1 over beta minus alpha. If x is between alpha and beta. And probability would be 0 otherwise. For every number outside the interval, there's no chance to be chosen, so their probability must be 0. For any number outside the interval, the chance of choosing those numbers are 0, so it's 0 otherwise. This is a probability function. And the support of x the set of all possible values that x could be. Since we're choosing x from the interval, x represents a value chosen from the interval alpha to beta. X could be anything in the interval. X could be any value on the interval. So support of x is the interval from alpha to beta. Since x represents a randomly chosen number on the interval, x could be any number on the interval. That's the support of x. the notation here. For the notation, we say X is a uniform distribution. The perimeter is an interval from alpha to beta. We write alpha beta represent the boundary. Alpha beta represent the boundary of this interval. The perimeters are alpha and beta. Alpha and beta represent the boundary of this interval. That's the notation for uniform distribution. Sometimes we just write, sometimes to make it easier, we can write X is U. Use U represent uniform. Alpha beta. Sometimes we use U represent uniform distribution. Use U represent continuous uniform distribution. For discrete uniform distribution, we must find a full name. But for continuous uniform distribution, we can only write uniform or U represent continuous uniform distribution. For discrete uniform distribution, we must find a full name, discrete uniform. But for continuous uniform, we just write uniform distribution from A to B, from alpha to beta. Next, let's look at an example here. Let X have a continuous uniform distribution from 1 to 5, from the interval from 1 to 5. Find each of the following probabilities. Part A, probability that S is between 2 and 4. Part B, probability that S is less than 3. Part C, probability that S is greater than or equal to 4. Part D, probability that S is equal to 2. Let's set down the problem first. First step, try to find the probability function. First step, try to find a probability density function. Here, this X is continuous random variable. We must find a probability density function. Find the probability density function first. F of X is 1 over beta minus alpha. Here, number 1 is alpha, number 4 is beta. Beta minus alpha is 4. F of X is 1 over beta minus alpha if X is between alpha and beta. So F of X equal to 1 over 4 if S is from 1 to 5 and 0 otherwise. This is the probability density function. This is the probability density function of X. Support of X is the interval from 1 to 5. It's a closed interval from 1 to 5. Now based on this, answer the question. Part A. What's the probability that S is between 2 and 4? What's the probability that S is between 2 and 4? For probability S between 2 and 4, take integral from 2 to 4. For S is between 2 to 4, S is between 1 and 5. For S is between 2 to 4, S is also between 1 and 5. So we use the function 1 over 4 here. F of X is 1 over 4 dx. Take antiderivative for 1 over 4. Antiderivative of 1 over 4 is 1 over 4x. Evaluate from 2 to 4. If I plug in 4, I get 4 over 4. If I plug in 2, I get 2 over 4. And together, that's 2 over 4, which is half. That's part A. Part B. What's the probability that S is less than 3? The support is from 1 to 5. The support is from 1 to 5. If x is less than 3, we take integral from 1 to 3, f of x dx. The support is from 1 to 5. If x is less than 3, we take integral from 1 to 3, f of x dx. And then for integral from 1 to 3, That's between the interval 1 and 5. So use the first function. 1 over 4 dx. Take antiderivative. That's 1 over 4x. Evaluate from 1 to 3. If I plug in 3, I get 3 over 4. If I plug in 1, I get 1 over 4. 3 over 4 minus 1 over 4 is 2 over 4, which is half. Part C. What's the probability that S is greater than or equal to 4? Here the support is from 1 to 5. Support is from 1 to 5. If S is greater than 4, take to go from 4 to 5. F of x dx. The support is from 1 to 5. Support is from 1 to 5. So if S is greater than or equal to 4, take to go from 4 to 5. F of x dx. For the interval from 4 to 5, 4 to 5 is between the interval is in the interval 1 to 5 here. So use the first equation. Use the first part. When S is between 4 and 5, f of x is 1 over 4 dx. Take antiderivative, you get 1 over 4x from 4 to 5. If I plug in 5, I get 5 over 4. If I plug in 4, I get 4 over 4. 5 over 4 minus 4 over 4 is 1 over 4. Part D. What's the probability that S equal to 2? Since x is a continuous random variable, probability that S equal to any constant is 0. Since x is a continuous random variable, probability that S equal to any constant is 0. So that's the answer. Next example. Every morning, a school bus arrives school between 7:30 and 7:45 a.m. Assume at every moment between 7:30 and 7:45 a.m. the chance that the school bus arrives school is the same. Part A. What's the probability that the school bus arrives before 7:40 a.m.? Part B. What's the probability that the school bus arrives after 7:36 a.m.? Part C. What's the probability that the school bus arrives between 7:35 and 7:42 a.m.? Part D. What's the probability that the school bus arrives exactly at 7:40 a.m.? So, let's set down the problem first. School bus arrives school between 7:30 and 7:45, and we assume that at every moment, the chance that the school bus arrives is exactly the same. At every moment, the chance that the school bus arrives is exactly the same. So this is uniform distribution. The x represents the arriving time of the school bus. Measured in minutes. After 7 a.m. The x represents arriving time of the school bus, measured in minutes, after 7 a.m. Then, x has a uniform distribution. From 45, from 30 to 45, then X has a uniform distribution. X has a continuous uniform distribution from 30 to 45. Since we measure the time after 7, 30 represents 7:30, 45 represents 7:45. Since we measure the time in minutes after 7 a.m., 30 represents 7:30, 45 represents 7:45. So this X has a continuous uniform distribution from 30 to 45. Next, write down the probability function. Write down the probability density function. Since this X is continuous and non-variable, write down the probability density function. F of X is 1 over beta minus alpha. That's alpha, that's beta. Beta minus alpha is 15. If X is between 30 and 45. And 0 otherwise. Next, find the support. Find support of X. Since the bus can only arrive between 7:30 and 7:45, support of X is from 30 to 45. Since the bus can only arrive between 30 and 45, support of X is from 30 to 45. Now, based on this information here, answer the question. Part A. What's the probability that the school bus arrives before 7:40? What's the probability that the school bus arrives before 7:40? We're looking for the probability that the arriving time is before 7:40, which means X is less than 40. If bus comes before 7:40, it means it comes 7:39, 7:38, 7:36, which is less than 7:40. So the probability that the school bus arrives before 7:40 is probability that X less than 40, because X is measured in minutes after 7 a.m. X is measured in minutes after 7 a.m. 7:40 means 40 minutes after 7 a.m. That's part A. Probability that X less than 40. We know that the support is from 30 to 45. Support of X is from 30 to 45. If X is less than 40, we take integral from 30 to 40. Support is from 30 to 45. If X is less than 40, take integral from 30 to 45. From 30 to 40, f of X dx. When x is between 30 and 40, we use the function f of x equal to 1 over 15. When x is between 30 and 40, we use the function f of x equal to 1 over 15. So the integral from 30 to 40, 1 over 15 dx. Then take the antiderivative. We get 1 over 15x. Evaluate from 30 to 40. 1 over 15x. Evaluate from 30 to 40. If I plug in 40, I get 40 over 15. If I plug in 30, I get 30 over 15, which is 10 over 15. That's 2/3. So that's the answer to part A. Part B. What's the probability that the school bus arrives after 7:36? What's the probability that the school bus arrives after 7:36? So we're looking for probability that x is greater than 36. If the school bus is arrived after 7:36, means it can arrive at 7:30, 7:37, 7:38, 39, so on. S must be greater than 36. Since x is measured in minutes after 7 o'clock, So x must be greater than 36. Support is from 30 to 45. If s is greater than 36, take integral from 36 to 45. F of x dx. For x between 36 and 45, we use the first part of the function. F of x is 1 over 15. When s is between 36 and 45, we use f of x equal to 1 over 15. Then take an antiderivative. That's 1 over 15x. Evaluate from 36 to 45. If I plug in 45, I get 45 over 15. If I plug in 36, I get 36 over 15. Then 45 minus 36 is 9. 9 over 15. If I reduce it, that's 3/5. So the chance that the school bus arrives after 7:36 is 3/5. That's the answer to part B. Now part C. What's the probability that the school bus arrives between 7:34 and 7:42? We're looking for probability that S is between 34 and 42. 34 and 42 is between the support, it's inside the support. So we can take integral from 35 to 42. F of x dx. Well, S is between 34 and 42. Well, S is between 34 and 42. F of x is 1 over 15. So f of x is 1 over 15. Dx. Then take an antiderivative. I get 1 over 15x. Evaluate from 35 to 42. If I plug in 42, I get 42 over 15. If I plug in 35, I get 35 over 15. Then subtract, I get 7 over 15. That's the probability that school bus arrive between 7:34 and 7:42. That's the answer to part C. Part D. What's the probability that the school bus arrive exactly at 7:40? So part D, we're looking for probability that x equal to 40. We're looking for probability that the school bus arrive exactly at 7:40. Now, since x is a continuous random variable, the probability that s equal to any constant is 0. Since x is a continuous random variable, the probability that s equal to any constant is 0. So the probability that the school bus arrive at 7:40 is exactly 0. The probability that school bus arrive exactly at 7:40 is 0. For any continuous random variable, the probability that s equal to any constant is always 0.